All right, today's question is first bad version. So this question, they phrase it as a story. We are developing some sort of software, and at some point at version n, we've found out that this version is bad, and we want to find out when exactly did this start happening. So the only thing we are allowed to access is this is bad version API call, but this is a very expensive call, so you want to limit our calls to this. So that means a simple solution such as just querying every single version from version 1 until we see the first bad version. While it works, it's not very efficient because we're making this many calls to is bad version to figure out the answer. So another way we can do this is we can try some sort of binary search. So in binary search, what happens is we kind of probe the middle. And then from here, this gives us a lot of information, right? So if this is a bad version, then that means the first bad version must exist somewhere to the left of it, right? So maybe we probe here. And then from here, we find that it's a good version. So that means the first bad version must be somewhere to the right of it. So let's probe the middle of that again. And then here we finally find the first bad version. Okay, so there's two ways of implementing this binary search. We're going to go over both of them and then see why one is better than the other for this specific scenario where is bad version is a very expensive call. Okay, so in binary search, we have some sort of a starting window and an end window. That way we can find out where the middle is to probe. So let's start with that. And start equals the first version, and then the end will be the last version. So while they still make sense, so start is always less than or equal to end, we'll probe the middle. And the middle will be start plus and minus start divided by 2. So this gives us a middle version. And now we have to test, is this a good or a bad version? So if is bad version middle. Okay, so let's say it's a bad version. Well, how do we know the difference between, probing this bad version versus probing this bad version, which is the answer? So you can see that in the answer, in the first bad version, the previous version must be good. So that means if the previous version is good, so if it's not a bad version, then we found the first bad version and we can return that version. But you can also see here that we have middle minus 1, so that means we should handle the edge case where middle is the first version. That's the case where everything is bad. So we have something like this. In that case, if middle is equal to 1, then that's also the correct answer. And we don't need to check the previous version because there is no previous version. Okay, so that handles our edge case. So what happens if this condition is not true? Well, then that means the previous version is also bad. So we want to limit our window. So that means we're in this case. And then what we want to do is we want to restrict our window so that for the next iteration, we're only searching over this window. So here we'll have, let's see, end will be equal to middle minus 1. So here we restricted our end, so this into here. Okay, but what if the middle version that we probe is actually good? Well, that means the first bad version must be somewhere to the right of this. So what we'll do here, this else, our starting window will become middle plus 1 instead. So we'll shift our starting window up here and blank all of these one out, and then do our next iteration with this instead. Okay, and then we're guaranteed that there's always a bad version because that's how the question is defined, that the latest version fails. So there must be a bad version somewhere. So this should always return. But just in case we made a mistake, we can do a return -1. So if we see a -1, we know that we made a mistake in coding this out. Okay, let's see. Just need to comment this out. Let's try that again. Cool. So this is actually not the most optimal way of solving this question. And this comes from the fact that in a single loop, at the worst case, we are actually doing two probes to figure out if this is the answer. So that means, if this is our worst case, where everything is bad, then how this algorithm would run is we would probe the middle. So let's say the middle is here. Then we would check the previous version. And then from that, we would limit our window and we'd run this as the next iteration. Maybe we'd probe these two. And then from here, this will be our next one. And then we probe these two. And then finally, we have a single element, and then we probe it, and then we hit the middle equals 1 case, and then we return middle. So you can see here we've actually probed a total of 1, 2, 3, 4, 5, 6, 7. So 7 calls. Now, what's another way to solve this problem instead of having to probe the previous version? Well, we're guaranteed that there's at least one bad version. That means at some point when we limit our window and we have a single element left, this has to be the bad version. So instead of checking the current version and the previous version, what we could check instead is if our window size is only a single element. So that means for the same worst case, if we code our binary search this way, what it would look like is you would probe the middle once. You would have something like this. You probe the middle again, and you have something like this, and you probe it one more time. So maybe from here we have that, and then we probe it again, and then finally we have a single element left, and now we're done. So in this version, let's see how many times we've probed. We've only probed 4 times. So you can see that in the worst case, this method of solving the question is a lot better than here, where we're probing twice, which is almost double the amount of calls. Now, the good news about this case is, let's say we have a perfect scenario, something like that, and we happen to probe the middle, and then we check the previous version. That means within 2 calls, we are done. So this is the benefit of the code that we just wrote, but you can see that the worst case, it gets pretty bad. We almost do double the calls of writing our binary search in this way. Okay, so for our second version, let's try and write our binary search this way instead. So in this way, some changes we have to make. One, it's not going to be start less than or equal to n, because we want to stop when there's a single element left. So that means n will always be bigger than start. So we also probe the middle. And let's see. So if it's the bad version, instead of doing this secondary check, we'll just automatically shift the end window. But here, instead of middle minus 1, we're only going to shift it by middle. So that's the case for if we have something like this, and turns out that we probe here. We don't want to do end or middle minus 1, because that would result in an array like this, and we'll never be able to find the answer here. So we always want to include the end. So not the end, sorry. The end should always include this middle probe. So that's the big change that we want to make here. And then at the very end, what's going to happen is the only way for this loop to exit will be because start is going to be greater than or equal to end. So at that point, we can return start. Okay, so let's give this one a go. So this is, instead of exiting early, we're going to wait until our window becomes small enough where there's only a single element, and that element has to be the bad version. Now, anytime that we're doing this, there's always some sort of a fear of what if end equals middle? Because if that's the case, then every time we hit here, we're going to run into an infinite loop. So let's see if that case can actually happen. So here we're calculating middle like so. Int middle equals start plus end minus start divided by 2. And our while loop gives us the guarantee that end is always greater than start. Okay, and we're worried about this case being true, so let's see if that can happen. So let's move some variables around. That means middle minus start is equal to end minus start divided by 2. And if this case was true, if n equals middle, then this becomes end minus start equals end minus start divided by 2. And then you can see here that the only way for n minus start to be equal to n minus start divided by 2 is if n minus start is equal to 0. But this cannot happen because we're guaranteed by the while loop that end is always bigger than start. So that means if we subtract them, they can't equal 0. So that means we've guaranteed that we're not going to run into an infinite loop in this while loop, and that we're always going to exit. And with this exit, we're going to end up with the answer, which is why this is accepted. Okay, that's the end of today, and I'll see you on the next one.